Okay, hi everyone, welcome back to this video series on Cisco ASA Firewall Troubleshooting RIP. This section includes several commands and techniques that you can use while troubleshooting different issues that may arise through your deployment of RIP. A number of scenarios are provided to exemplify these troubleshooting techniques. Scenario 1, RIP version mismatch. Using the same network topology illustrated in figure 512, the internal router was intentionally configured with the incorrect RIP version. The Cisco ASA was configured with RIP version 2 on the inside interface as previously shown, and the internal router was configured with RIP version 1. The output of the show route command does not display any routes learned via RIP. Example 5.7 shows the output of this command. The debug command, debug RIP events, is used as a troubleshooting tool for this problem as demonstrated in example 5.9. In the highlighted line, the Cisco ASA displays an error message indicating that the router 10.10.1.2 is sending an incorrect RIP version v1. The solution to this problem is to configure RIP version 2 on the internal router. Example 5.10 shows the output of the debug RIP events messages when the correct information is received from the inside router. So you can see here example 5.10 output from the debug RIP events showing correct RIP version during negotiation. Notice that the Cisco ASA receives the RIP version 2 update from the router 10.10.1.2 on the inside interface. Additionally, the routes learned are also displayed. Scenario 2, RIP authentication mismatch. The topology shown in figure 512 is also used in this example. The internal router and the Cisco ASA were configured to perform RIP authentication using MD5. The MD5 password was configured incorrectly on the inside router R1. Example 5.11 shows the output of debug RIP events on the Cisco ASA, which shows that there is a problem with MD5 authentication. Scenario 3, multicast or broadcast packets blocked. RIP v1 uses broadcast packets and RIP v1 uses broadcast packets and RIP v2 uses multicast packets. If broadcast or multicast packets respectively are blocked, the Cisco ASA will never be able to successfully establish a RIP neighbor relation with its peers. The debug RIP events command is also useful to troubleshoot this problem. Example 5.12 shows the output of debug RIP events while RIP v2 multicast packets were being blocked. As you can see from this example, the Cisco ASA is sending RIP v2 packets to the address 224.0.0.9 without receiving anything back from its peers. You will also see this behavior when RIP is not enabled on any other routing device on that segment. OSPF. The OSPF routing protocol was drafted by the IGP working group of the Internet Engineering Task Force IETF. It was developed because RIP was not able to scale for large heterogeneous networks. The OSF specification is defined in RFC 2328. OSPF version 2 is based on the shortest path first algorithm, usually referred to as the Dijkstra algorithm after its author. OSPF is a link state routing protocol. It sends the Dijkstra algorithm Okay. It sends information about attached interfaces, metrics used, and other variables to its peers or neighbors. The information is called link state advertisements, LSAs. They are sent to all the peers within a specific hierarchical area. OSPF operates in hierarchies of separate anonymous systems. These autonomous systems can be divided into groups of contiguous networks called areas. Routers that are part of more than one area are referred to as area border routers, ABRS. Figure 5.15 illustrates an example of this concept. As shown in figure 5.15, more than one OSPF area can be joined together by an ABR. On the other hand, an OSPF backbone, OSPF area 0 must be present to propagate routing information to all other areas. The Cisco ASA can be configured to act as an ABR. If they can provide, it then can provide not only connectivity but also security while performing LSA filtering. Type 3 LSAs refer to summary links and are sent by ABRs to advertise destinations outside an area. The OSPF ABR Type 3 LSA filtering feature gives the user improved control of route distribution between OSPF areas. This feature also provides the capability of hiding the private networks by using network address translation, NAT, without advertising them. Figure 5.6 provides an example of how the Cisco ASA can be configured as an ABR and provides LSA Type 3 filtering. The following sections provide different sample configurations explaining all OSPF features supported by Cisco ASA. So you can see here in figure 5.15, areas in OSPF. Figure 5.16, Cisco ASA LSA Type 3 filtering. Configuring OSPF. Cisco ASA supports several OSPF features and capabilities. The following summarizes the Cisco ASA OSPF support: intra-area, inter-area, and external Type 1 and Type 2 routes. Support to act as a designated router, DR. Support to act as a backup designated router, BDR. Support to act as an ABR. Support to act as an ASBR with route redistribution between OSPF processes, including OSPF static and connected routes, virtual links, OSPF authentication, both clear text and MD5 authentication, stub areas and not so stubby areas, NSSAS, LSA flooding, ABR Type 3 LSA filtering, OSPF, neighbor command and dynamic routing over VPN, load balancing between a maximum of 3 peers on a single interface using equal cost, multi-path ECMP routes, enabling OSPF. The topology illustrated in figure 5.17 is used in this example. It includes a Cisco ASA connected to a router named R1 on its inside interface. This router is also connected to 2 other routers, R2 and R3. In the first example, the Cisco ASA R1, R2, and R3 are all configured in area 0. To initially configure OSPF, configure these tasks. Step 1, log into ASDM, navigate to configuration, device setup, routing OSPF, and setup. Step 2, the Cisco ASA supports up to only 2 OSPF process instances on its configuration. Each OSPF process has its own associated areas and networks. To enable an OSPF process, select Enable this OSPF process for one of the 2 available processes as shown in figure 518. In this example, the OSPF process 1 is used. Step 3. Under the OSPF process ID field, enter a unique numeric identifier for the respective OSPF process. In this example, the process ID is the number 1. The Cisco ASA uses this process ID internally and does not need to match the OSPF process ID on any other routing device. You can select any value from 1 to 65535. Step 4, optional. You can click on the Advanced button to configure additional OSPF parameters such as the router ID, adjacency changes, administrative route distances, timers, and default information originate settings. The Edit OSPF Process Advanced Properties dialog box shown in figure 519 is displayed. Figure 519 shows the default options. In this example, the default values are configured for simplicity. Step 5. Configure the area properties, the area network for the OSPF process by navigating to Area Networks tab. Step 6. Click Add to add the specific networks. The screen is shown in figure 520. Step 7. Select the OSPF process you want to edit. In this example, the OSPF process 1 is used. Step 8. Enter the area ID in the area ID field. In this example, area 0 is used. However, area values range from 0 to 4294967295. You can also enter the area ID using an IP address. Step 9. There are 3 different area types. Normal makes the area a standard OSPF area. This is the default option when an area is initially created and the one used in the example. Stop makes the area a stop area. Stop areas stop AS external LSAs, type 5 LSAs from being flooded into the stop area. When you create a stop area, the summary checkbox is available. You can prevent summary LSAs type 3 and 4 from being flooded into the area by not selecting the summary checkbox. NSSA makes the area not a so stubby area. NSSA areas accept type 7 LSAs as with stop area configuration. You can uncheck the summary checkbox to stop summary LSAs from being flooded into the area. Route redistribution can also be disabled if you don't select the redistribute checkbox and do enable default information originate. The default information originate option enables the Cisco ASA to generate a type 7 default into the NSSA. This option is disabled by default. You can also specify the OSPF metric value for the default route in the range from 0 to 167777214. The default value is 1. The metric type option is used to specify the OSPF metric type for the default route. You can select the number 1 for type 1 or 2 for type 2 if default information originate is configured. the default value is 2. Step 10. Define the networks in the area by entering the IP address and the mask of the networks under the area network section. In this example, the 10.10.1.0/24 network is added. Step 11. Click the Add button to add the network defined in the Enter IP address and Net Mask sections to the area. These networks appear in the Area Networks table. Example 5.3 shows the CLI commands generated by ASDM and sent to the Cisco ASA. The router OSPF command is used to enable OSPF and define the OSPF process. The number one is used as identification parameter for the OSPF routing process. The network command specifies the interfaces that will run OSPF. Furthermore, it specifies the area to be associated with that interface. You can use the network address or the address of the interface where you want to enable OSPF. Example 5.14 shows the output of the root show inside command after OSPF was configured in the Cisco ASA. So you can see here example 5.14 output of the show route command. The show OSPF command can be used to display the general information about the OSPF routing process. Example 5.15 shows the output of the show OSPF command in the Cisco ASA. So I'm going to leave it here this evening for this video. If you like listening, please consider like, sharing and subscribing. Thank you.